Pick up something solid near you, a cup or a coin, and press your thumb against the surface. It feels single and firm exactly where it is. You can tell yourself a simple story about what it is made of. Tiny grains of stuff, and inside those, smaller grains, down and down until you reach the smallest possible speck, a little ball of matter that cannot be cut any finer. That speck is the thing we've been wrong about. The smallest pieces of you and that cup are not little balls of stuff. Each one is a ripple in a field that fills all of space, closer to a sound than to a stone. Physicists call this quantum field theory, our best account of what the world is made of. We will build it slowly, one plain step at a time, starting with an easy question. What is the smallest piece of anything? If you would like to come along, take a moment to subscribe and we will begin. Hold a single grain of salt on the tip of your finger. It is small, but you can still see it, a tiny white cube catching the light. Now imagine cutting it in half, and then in half again, and again, far past what your eyes or any knife could manage. Most of us carry a quiet belief about where this cutting ends. We feel that somewhere down there, after enough halving, you would reach a piece so small it simply could not be divided any further. A final grain, a solid speck of stuff, perfectly itself sitting at the bottom of everything. That belief is very old, and for a long time it was the best guess anyone had. The man usually given credit for it lived in Greece about 2,400 years ago. His name was Democritus, and he taught alongside an older thinker named Leucippus. Democritus had a cheerful reputation, remembered by later writers as the laughing philosopher, a man amused by human folly. His idea was simple and bold. If you keep dividing any object, you cannot go on forever. At some point you reach pieces that cannot be split. He called them atomos, a Greek word meaning uncuttable. Between these uncuttable pieces, he said, there was nothing at all, only empty space for them to move through. Everything you see in his picture was just atoms and void, arranged in different shapes and clusters. It is worth sitting with how much this small idea was asked to carry. Water flowed, in his telling, because its atoms were smooth and round and rolled past one another. Iron held firm because its atoms were rough and hooked and caught on their neighbours. Taste, smell, warmth, all of it came down to the shapes of these tiny grains and the ways they fit together. There were no experiments behind this, no instruments, no measurements. It was reasoning carried as far as a careful mind could take it, and for a guess made with the naked eye alone, it pointed in a remarkably right direction. The picture that Democritus drew is the one most of us still hold without noticing. A particle in this everyday image is a tiny ball of matter. It has a size, even if a vanishingly small one. It sits at a definite place. It is hard in the sense that it is made of solid stuff all the way through, with no inside left to explore. When you imagine the smallest piece of the salt on your finger, this is almost certainly what you see. A miniature marble, complete and indivisible, the last stop on the long road of cutting. Honour that picture for a moment, because it served brilliantly for a very long time. It is intuitive. It matches the way solid things feel under your hand. It even survived the birth of modern chemistry, when the word atom was handed to the small units that combine to form water and salt and air. For more than 2,000 years, the smallest grain of stuff was the working answer to the oldest question about matter, and almost no one had a reason to doubt it. But a guess, however good, is not yet knowledge. Democritus had no way to test his atoms, and the truth is that he was right about the wrong thing, and wrong about the right thing in ways that took centuries to untangle. The pieces he imagined as final turned out to have insides. The hardness he imagined as solid matter turned out to be mostly empty, and the very idea of a tiny ball sitting somewhere definite would slowly come apart under the pressure of real evidence. So we begin where everyone begins, with the solid speck, the last uncuttable grain. The question that drives everything ahead is the one Democritus could only answer by reasoning. What is the smallest piece of anything, really, and what happens when we finally find a way to look? For more than 2,000 years after Democritus, the atom stayed an idea rather than a measurement. That changed slowly, and it changed first in the hands of chemists who were not even trying to find the smallest grain of stuff. They were trying to make sense of what happens when substances combine. The key figure here is John Dalton, an English school teacher and weather watcher working in the early 1800s. Dalton was quiet, careful, and colourblind, a condition he studied so closely that it was once called Daltonism. What caught his attention was a pattern in chemistry. When two elements combine to make a compound, they always do it in fixed, whole number ratios by weight. Hydrogen and oxygen make water in the same proportion every time, never a little more or a little less. Dalton saw the cleanest explanation. Each element is made of identical small particles, atoms, each with its own fixed weight, and they join in simple whole numbers because you cannot use half of one. This brought Democritus's word back, but with something new attached. Now the atom had a measurable property, weight, and a job to do in real reactions you could run on a bench. Dalton's atoms were still tiny solid balls, indivisible and complete. He had no notion of any structure inside them. For most of the 1800s, that was the settled view. The atom was the bottom of the ladder, the final piece, exactly as the old guess had promised. The first crack came at the very end of that century in 1897, in a laboratory at Cambridge. The man at the bench was Joseph John Thomson, known to everyone as J.J. Thomson, a physicist with a gift for coaxing experiments out of stubborn equipment. He was studying cathode rays, a faint glow that streamed through a sealed glass tube when you ran a high voltage across it. No one was sure what the rays were. Some thought they were a kind of light. Thomson suspected they were something with mass, and he set out to test it. He did 3 patient things. He bent the rays with a magnet. He bent them again with an electric field. And from how much they bent, he worked out the ratio of their charge to their mass. The number stunned him. Whatever made up these rays was almost 2,000 times lighter than the lightest atom known, the hydrogen atom. And no matter which metal he used for the source, or which gas filled the tube, the rays were always made of the same light negatively charged thing. Thomson had found a piece smaller than the atom. We now call it the electron. This was the moment the uncuttable became cuttable. If a tiny negative particle could be pulled out of any atom, then the atom was not the final grain after all. It had parts. The bottom of the ladder dropped away, and there were more rungs below. Thomson, being careful, tried to picture how these new pieces fit inside the atom. He suggested that the negative electron sat scattered through a spread of positive charge, like raisins in a soft cake, or in the comparison that stuck, like plums in a pudding. The plum pudding model, people called it. It was a reasonable first sketch, and it would not last long, but that is not the point yet. The point is the size of the shift. For more than 2 millennia, the atom had been the smallest possible thing. In a single set of experiments, Thomson showed it was made of smaller things still. The solid speck had cracked open, and the obvious next question was waiting. If the atom has parts, then how exactly are they arranged inside, and what is holding them there? Thomson's plum pudding gave the atom an inside, but it was a soft, vague inside. The negative electrons floated in a haze of positive charge spread across the whole atom. It was a guess made in the dark, and it needed testing. The test, when it came, was one of the most elegant in the history of physics, and the answer it gave was so strange that the man who ran it could barely believe it. That man was Ernest Rutherford, a blunt, booming New Zealander working in Manchester, England. Rutherford had already won a Nobel Prize for his work on radioactivity, and he had a knack for asking nature a sharp question and forcing a clear answer. Around 1909, he set 2 younger colleagues, Hans Geiger and a student named Ernest Marsden, to a careful task. They would fire alpha particles, small fast positive bits thrown off by radioactive material, at an extremely thin sheet of gold foil and watch where they went. the expectation was gentle. If Thomson was right, the positive charge in the gold was spread out thin and soft. The heavy, fast alpha particles should sail almost straight through, nudged only slightly off course, the way a cannonball passes through fog. Most of them did exactly that. But Rutherford asked Marsden to look for any that came back, and a few did. About 1 in every several thousand alpha particles bounced sharply sideways, and a rare one came almost straight back toward the source. Rutherford later said it was as astonishing as firing a heavy shell at a sheet of tissue paper and having it bounce back and hit you. A soft spread of charge could never do that. To turn a fast, heavy particle right around something small, hard and powerfully concentrated had to be sitting in the way. Rutherford worked through the numbers and reached a picture that has stayed with us. Nearly all of the atom's mass and all of its positive charge is packed into a tiny core at the centre. He called it the nucleus. The light electrons occupy the vast space around it. The atom was not a pudding. It was almost entirely empty, with a dense speck at its heart. The scale of that emptiness is hard to hold in the mind, so reach for a comparison. If you grew an atom until its nucleus were the size of a marble set on the centre line of a large sports stadium, the electrons would be tiny specks drifting somewhere out near the higher seats, and everything between would be empty space. The nucleus carries more than 99.9% of the atom's mass, in a region thousands of times smaller than the atom itself. Matter, looked at this closely, is mostly nothing. This raises a question you can feel in your own hand. If atoms are this empty, why does the coin in your pocket feel solid? Why does your hand not pass through the table? The answer is not that the pieces are touching. They almost never touch. What you feel as solidity is force, not stuff. The electrons on the surface of your hand and the electrons on the surface of the table repel one another, pushing back before they ever meet. Hardness is electric resistance, felt through a wall of empty space. The firmness of the world is real, but it is held up by force, not by solid filling. So Rutherford left us with an atom that was a tiny dense nucleus surrounded by light electrons and a great deal of nothing. It was a stunning result, but it carried a new trouble inside it. Those electrons circling the nucleus should by the rules of the day spiral inward and crash in a fraction of a second. The atom should not be stable at all. Something deep was still missing, and finding it would mean rethinking light itself. To understand why Rutherford's tidy little solar system of an atom could not survive, we have to step away from atoms for a moment and look at something that seems unrelated. Glowing objects, a hot iron, a candle flame, the filament in an old bulb. At the turn of the 20th century, this ordinary question, the colour of glowing things, cracked physics open and let the strangeness pour in. The puzzle had a dull name, the blackbody problem, but a simple heart. Heat any object and it glows, first dull red, then orange, then white as it gets hotter. Physicists wanted a formula that predicted exactly how much light of each colour a hot object gives off. Every formula they tried agreed with experiment at some colours and failed badly at others. The most respectable theory predicted that a warm object should pour out an infinite amount of energy at the blue and ultraviolet end of the spectrum, which was plainly nonsense. Your fireplace does not blast you with ultraviolet. The mismatch was so absurd it was later nicknamed the ultraviolet catastrophe. In 1900, a careful conservative German physicist named Max Planck found a fix, and he disliked his own solution. Planck was not a revolutionary by temperament. He was a respectful man who loved the orderly physics he'd grown up with. But the numbers forced his hand. To make the formula match reality, he had to assume that a glowing object could not give off energy in any amount it liked. It could only release energy in fixed separate packets, small bundles whose size depended on the colour of the light. He called each bundle a quantum, from the Latin for how much. Planck treated this at first as a mathematical trick, a strange bookkeeping rule that happened to work. He spent years hoping someone would explain it away. No one explained it away. Instead, In 1905, a young patent clerk named Albert Einstein took the idea far more seriously than Planck had. Einstein was looking at a different puzzle, the photoelectric effect. Shine light on certain metals and they release electrons. The odd part was the details. Dim blue light could knock electrons free, while bright red light, no matter how intense, could not. If light were a smooth wave, brightness alone should eventually do the job. It did not. Einstein's answer was to take Planck's packets literally. Light itself, he proposed, is not a continuous wave but a stream of energy bundles, each one carrying an amount of energy set by its colour. Blue packets are energetic enough to knock an electron loose. Red packets, individually, are too feeble, and piling up more weak packets does not help, because each electron is freed by a single hit. We now call these packets of light photons. With this one move, Einstein explained the photoelectric effect cleanly, and it was largely for this, not for relativity, that he later received the Nobel Prize. Sit with what had just happened. Light, which everyone had spent a century proving was a wave, was now also arriving in countable lumps. A wave spreads out and fills space. A lump is here and not there. Light somehow did both, depending on how you questioned it. This is the first real crack in the solid speck story, but coming from the opposite side. The trouble was not that the tiny ball turned out to be a wave. It was that the wave turned out to come in countable pieces, and the piece turned out to behave like a wave. Energy was grainy. Light was grainy. And if light, the very thing we thought of as a smooth wave, comes in packets, a fair question turns back on matter itself. The photon behaves like a wave that comes in lumps. Could the electron, that little lump of matter, somehow behave like a wave? Light had turned out to come in lumps. The bold question that followed was the reverse one. If a wave like light can act like a particle, can a particle like the electron act like a wave? The man who dared to ask it plainly was not a famous professor, but a French aristocrat finishing his doctoral thesis, and his idea was so unexpected that his own examiners did not know what to make of it. His name was Louis de Broglie, a member of an old noble family who had come to physics by way of history before the puzzles of the quantum world pulled him in. In 1924, in his doctoral thesis, de Broglie made a leap of pure symmetry. Nature, he felt, should be balanced. If light, long thought a wave, also behaves as particles, then matter, long thought particles, should also behave as waves. He wrote down a simple relationship. Every piece of matter, he said, has a wavelength, and that wavelength gets smaller as the thing gets heavier and faster. This is why we never notice it. Run the numbers for a thrown baseball, and its wavelength is so unimaginably tiny, far smaller than a single atom, that no wave behavior could ever show. The ball is simply a ball. But run the numbers for an electron, which is fantastically light, and the wavelength comes out comparable to the spacing of atoms in a crystal. For an electron, the wave side of its nature is not hidden at all. It is right there, waiting to be seen, if only you knew where to look. De Broglie's thesis was so strange that his committee hesitated. They sent it to Einstein for an opinion. Einstein, who had taught the world that light comes in lumps, recognized a kindred boldness at once, and he praised it. With that backing, de Broglie passed, and the idea of matter waves entered physics. But an idea backed by Einstein is still only an idea. Matter waves needed to be caught in the act. The proof came, as good proofs often do, partly by accident. At Bell Telephone Laboratories in the United States, two physicists named Clinton Davisson and Lester Germer were firing electrons at a piece of nickel and watching how they bounced off. One day, a laboratory accident let air into their apparatus and ruined the nickel surface. To clean it, they heated the nickel strongly, and in doing so they accidentally turned the messy metal into a small number of large, neat crystals with atoms lined up in orderly rows. When they fired electrons at this newly ordered surface, the pattern changed completely. The electrons no longer scattered every which way. They came off strongly at certain special angles and were nearly absent at others. This is exactly what waves do when they pass through a regular grating. The rows of atoms in the crystal acted like the lines of a diffraction grating, and the electrons, behaving as waves, reinforced one another at some angles and cancelled at others. When Davisson and Germer measured the wavelength behind this pattern, in 1927, it matched de Broglie's formula closely. Take a moment with how odd this is. An electron is a thing you can count. You can catch one at a time, hear it click in a detector, treat it as a single solid object, and yet, sent at a crystal, a stream of these countable objects spreads and overlaps and cancels exactly as ripples on a pond would. The electron carries a wave with it, or in some sense is a wave, even as it stays a thing you can count one by one. So the strangeness was no longer confined to light. Matter did it too. The little ball of the old picture had a wave wrapped around it, or built into it, and once you accept that an electron is somehow a wave, a sharper and more troubling experiment becomes possible, the one that more than any other refuses to let the solid speck survive. We send the electrons not at a crystal, but at a wall with two narrow slits. The double-slit experiment is the one many physicists would name if you asked them for the single strangest result in all of science. Richard Feynman, who helped build the modern theory, said it holds the only real mystery of quantum mechanics, and that everything else follows from it. It begins as a simple setup, and it ends somewhere your everyday intuition cannot follow. Start with the picture for ordinary waves, because it makes the rest readable. Imagine a calm pool of water and a barrier across it with two narrow gaps. Send a straight wave toward the barrier. Two new circular waves spread out from the two gaps, and where they overlap they interfere. Where two crests meet, the water rises high. Where a crest meets a trough, they cancel and the water goes flat. On a screen beyond the barrier you get a striped pattern, bands of strong motion separated by bands of stillness. This is the unmistakable signature of waves passing through two slits. Light does it too. Thomas Young showed exactly this with light at the start of the 1800s, and his bands were strong evidence that light is a wave. Now do it with electrons. Fire a beam of electrons at a barrier with two narrow slits, and let them land on a detecting screen behind it. If electrons were simply tiny balls, you would expect two bright stripes, one behind each slit, where the little balls pass through. Instead, you get the striped interference pattern, many bands, exactly as if each electron were a wave passing through both slits at once, and interfering with itself. The wave nature we met with the crystal shows up here in full. That alone is strange. But here is the part that undoes the solid speck. Turn the beam down. Send the electrons one at a time, so feeble that only a single electron is in the apparatus at any moment, with long gaps between. Each electron arrives at the screen as a single point, a single tiny flash, countable and definite just as a particle should. There is no spread out splash, one electron, one dot. And yet, as the dots accumulate over hours, one lonely electron after another, they do not pile into two stripes. They slowly build up the full banded interference pattern, the same pattern you would get from a wave going through both slits. Sit with this, because it deserves a moment of stillness. Each electron goes through the slits alone, with no other electron to interfere with. It lands as a single dot. But the collection of these solitary dots arranges itself as though every single electron somehow went through both slits and interfered with itself on the way. A single particle, on its own, produces the pattern of a wave passing through two openings at once. The natural reaction is to want to catch it in the act. Put a small detector at each slit and simply watch which one each electron really goes through. When you do this, the experiment changes. With detectors watching, each electron is found to go through one slit or the other, like a sensible particle, and the banded pattern vanishes. You get two plain stripes. The act of finding out which path was taken erases the wave behaviour. Stop watching, and the bands return. No comfortable picture survives this. The electron is not a tiny ball that quietly takes one path. It is not simply a wave either, since it always lands as a single dot. It behaves as if it explores all the possibilities at once, until something forces it to commit to one. What is the thing that travels through the apparatus between launch and landing? It is not a ball, and it is not quite a wave. To even describe it, physicists needed a new kind of object, something that could carry these spread out possibilities. That object is the wave function. The double-slit experiment leaves us needing to describe something that is neither a tidy ball nor a simple ripple, something that spreads through both slits yet lands as a single dot. Physicists found a way to write that something down. It is called the wave function, and it is the central character of quantum mechanics. Understanding what it is and what it is not is the next careful step. The wave function arrived in 1926 from an Austrian physicist named Erwin Schrödinger. Schrödinger was a cultured, restless man, fond of poetry and philosophy, and he wrote his great equation during a working holiday in the Swiss Alps. Taking de Broglie's matter waves seriously, he asked what equations such a wave would obey, how it would change and move and bend around obstacles. The result, now called the Schrödinger equation, is to quantum physics roughly what Newton's laws are to ordinary mechanics. Give it the forces acting on a particle, and it tells you how the particle's wave evolves, smoothly and predictably, moment to moment. But this raised a hard question that Schrödinger himself wrestled with. A wave of what? For water, the wave is a rising and falling of water. For sound, it is a squeezing and stretching of air. What was waving in his electron wave? Schrödinger first hoped the electron was literally a little spread-out cloud of charge, smeared into the shape of the wave. That picture quickly ran into trouble, because the wave spreads out wider and wider over time, while a real electron is always caught at a single point, never as a smear. The reading that survived came from another German physicist, Max Born, also in 1926. Born proposed something subtle and at first deeply unsettling. The wave function is not the electron spread out in space, it is a map of probability. Where the wave function is large, you are likely to find the electron if you look. Where it is small, you are unlikely to find it. Where it is zero, you will never find it. The wave does not tell you where the electron is. It tells you the chance of each possible place you might catch it. This is why the double-slit pattern works the way it does. The wave function of each electron genuinely passes through both slits and interferes with itself, building up regions where finding the electron is likely and regions where it is forbidden. But when the electron actually lands, it lands at one single spot, chosen with the odds the wave function lays out. Many electrons, each landing by these odds, slowly trace the bright and dark bands. The bands are a picture of probability made visible, one dot at a time. There is a sharp edge to this idea, and it is worth naming plainly rather than dressing up. Before you look, the wave function does not say the electron is secretly at one definite place you simply have not checked. As far as every experiment can tell, the electron does not have a single position until it is detected. The wave function is the fullest description there is, and it speaks only of chances. Einstein hated this. He felt the universe could not run on dice, and he argued against it for the rest of his life. But the probabilities have been tested to extraordinary precision, and they hold. So the thing moving through the apparatus is not a ball and not a classical wave. It is a wave function, a spread of possibility that evolves smoothly and predictably until a measurement pins it to one outcome with a definite chance. The solid speck is now gone in all but memory. In its place is a strange new object that is somehow everywhere it might be at once. And this spreading carries a built-in cost. If a particle has no single position until you look, then position and motion can no longer both be perfectly sharp. That limit has a name, and it is the next step down. The wave function tells us a particle does not sit at one definite place until it is measured. Press on that idea and it leads somewhere unavoidable. If position is fuzzy, what about motion? It turns out the two are tied together by a rule that is not about clumsy instruments or careless measurement. It is woven into the nature of things, and it is called the uncertainty principle. It came in 1927 from Werner Heisenberg, a brilliant young German physicist, then in his 20s, who had already built an early version of quantum mechanics out of pure mathematics. Heisenberg's principle says that certain pairs of properties cannot both be known sharply at the same time. The most famous pair is position and momentum, where momentum means how much motion a thing carries, its mass times its velocity. The sharper you know where a particle is, the blurrier its momentum becomes, and the sharper you know its momentum, the blurrier its position. You can trade one for the other, but you can never make both perfectly precise at once. It is easy to mishear this as a statement about our tools, as if the particle really does have a sharp position and a sharp motion, and we are simply too clumsy to catch both. That is not what the principle says. The blur is real. A particle with a very well-defined momentum genuinely does not have a definite position. It is spread out. The uncertainty is in the thing itself, not only in our knowledge of it. You can see why this must be true once you accept matter waves. Think about what a wavelength is. To measure a wave's wavelength precisely, you need a long, even train of ripples, many crests in a row, spread over a wide stretch. But a wave spread over a wide stretch does not have a single location. Now go the other way. To make a wave that is sharply located in one spot, a single tight pulse, you have to add together many different wavelengths. A sharp location smears the wavelength, and since wavelength sets momentum, a sharp position smears the momentum. Position and motion pull against each other because the thing is a wave, and no wave can be both perfectly narrow and perfectly steady at once. Heisenberg even put a number on the trade. The uncertainty in position multiplied by the uncertainty in momentum can never drop below a tiny fixed amount, set by Planck's constant, the same small number that first showed up in the packets of light. That constant is the size of the graininess of the quantum world. It is fantastically small in everyday units, which is exactly why you never notice this trade for a thrown ball or a moving car. Their uncertainties are real, but so minuscule that the world looks perfectly sharp. For an electron, the constant is not negligible at all, and the blur runs the show. This is not a small footnote. It reaches into how the world is built. Recall Rutherford's worry that electrons should spiral into the nucleus and atoms should collapse. The uncertainty principle is part of what saves them. To pin an electron right onto the tiny nucleus would mean knowing its position extremely sharply, which would force its momentum to be enormous, and that huge motion would fling it back out. The electron settles into a balance, spread into a cloud around the nucleus, held between falling in and flying out. The very stability of matter, the reason atoms hold their size, leans on this refusal to be pinned down. So the particle has lost another piece of its old solidity. It does not have a sharp place and a sharp motion at the same time, not because we cannot measure well, but because those sharp values do not exist together. And there is one more built-in property, stranger than the rest, that the little ball cannot account for. The electron behaves as though it carries its own fixed inner twist, a thing called spin. By now the particle has lost its sharp position and its sharp motion. There is one more property it carries that the little ball simply cannot explain, and it is the strangest of all because it sounds so ordinary. It is called spin. The name is a trap because nothing is actually spinning, and the story of how physicists learned that is worth telling slowly. The first hint came in 1922, in an experiment by two German physicists, Otto Stern and Walter Gerlach. They sent a thin beam of silver atoms through a specially shaped magnetic field and onto a screen. Their thinking was about magnetism. An electron moving in an atom acts like a tiny magnet, and a tiny magnet passing through an uneven magnetic field should get pushed, deflected up or down depending on how it is oriented. If the orientations were random, as everyone expected, the beam should smear into a single broad band on the screen, with all the in-between angles filled in, That is not what happened. The beam split cleanly into two separate spots, one deflected up and one deflected down, with nothing in between. The little magnets were not pointing every which way. They were allowed only two settings, up or down, and nothing else. There is a charming detail in how the result became visible. Stern was a cigar smoker, and the cheap cigars he could afford were rich in sulphur. When he breathed over the screen while examining it, the sulphur in his breath reacted with the faint silver deposit and turned the two spots dark and clear. A frugal habit helped reveal one of the quantum world's sharpest surprises. The two-spot result meant some property of the electron comes in only two values. A few years later, two young physicists, Samuel Gaudsmit and George Uhlenbeck, gave it a name and a picture. They proposed that the electron carries its own built-in angular momentum, as though it were a tiny ball spinning on its axis, and that this inner rotation makes it a small magnet. They called it spin, and the name stuck even though the picture behind it does not survive scrutiny. Here is why the picture fails. If the electron were a literal spinning ball of its known size, its surface would have to move faster than light to produce the magnetism we measure, which is impossible. And the electron, as far as any experiment can tell, has no size at all to spin. So spin is not rotation. It is a genuine intrinsic property of the electron, as basic as its mass or its charge, a fixed amount of angular momentum that the electron simply has built in, with only two possible orientations when you measure it. The everyday word points at something real, but the real thing has no everyday equivalent. The electron is a magnet with a built-in two-sidedness, and that is the honest end of the description. Spin turned out to be far more than a curiosity, because of a rule worked out by the Austrian physicist Wolfgang Pauli in 1925. Pauli, famous for his sharp tongue and sharper mind, found that no two electrons in an atom can share the exact same quantum state, including their spin. This is the exclusion principle, and it is the reason matter has structure. Electrons cannot all pile into the lowest level around a nucleus. They must stack into shells, two to a level by their opposite spins, then filling outward. That stacking is the origin of the entire periodic table, the reason elements differ, the reason chemistry exists, the reason the world has variety at all. So a property with no everyday counterpart, a twist that does not turn, ends up shaping every substance you have ever touched. The little ball cannot hold spin, cannot hold exclusion, cannot hold any of it. The failures have piled high enough now to gather and face directly. We have been pulling threads loose one at a time. Now it helps to stop and lay them side by side, because the case against the solid speck is strong enough that we should look at the whole of it before we set the picture down. This chapter does no new experiment. It gathers what the experiments have already shown. Start with where we began. The atom was supposed to be the smallest, uncuttable grain. Thomson pulled the electron out of it, and the grain had parts. Rutherford found that those parts surround a tiny dense nucleus, and the atom turned out to be almost entirely empty, its solidity made of force rather than stuff. Already the everyday image, a small ball of solid matter, was in trouble at the level of the atom. But the deeper trouble was waiting at the level of the electron itself, the thing we had hoped would be the real final speck. Take the electron and ask the simple questions you would ask of a tiny ball. Where is it? The wave function answers that before you look, it has no single place. It is a spread of possibility, genuinely passing through both slits in the double-slit experiment and interfering with itself, landing as one dot only when measured. A ball is somewhere. The electron, until caught, is not. Ask how fast it is going and where it is, both at once. The uncertainty principle answers that you cannot have both sharply, and not because your instruments are poor, but because those sharp values do not exist together. A ball has a definite position and a definite velocity at every instant. The electron does not. Ask whether it is a wave or a particle. The lumps of light and the diffraction of electrons answer that it is neither or both, depending on how you question it. Sent through a crystal or two slits, it spreads and interferes like a wave. Caught in a detector, it arrives as a single countable click. A ball is always a ball. The electron changes its face with the question. Ask what it is made of inside. Probe the electron as hard as our best machines allow and it shows no size and no parts. It behaves as a point with no interior, yet it carries definite mass, definite charge, and a built-in spin that cannot be a real rotation because there is nothing of any size to rotate. A ball has an inside. The electron so far has none. Put these together and the everyday picture does not merely need adjusting. It fails at every point you test it. The electron is not small and solid, not located until measured, not simultaneously sharp in place and motion, not a wave, not a particle, not possessed of an inside. Each property of the little ball, examined closely, turns out to be wrong. The picture that served for 2,000 years has run out of road, and yet the electron is utterly real. It is countable. It makes a definite click. It has a precise mass and charge measured to many decimal places. It builds every atom and carries every electric current. Whatever it is not vague or fuzzy in its existence. It is sharply, reliably there. So we are left with a hard demand. We need a picture that keeps everything real and definite about the electron, its countability and its exact properties, while throwing out the little ball entirely with its size, its single location, its solid inside. That is a tall order, and no patching of the old image will meet it. The fix is not a better ball. It is a different kind of thing altogether, an object already familiar from another corner of physics, one that can be spread out and countable at the same time. To find it, we set the spec gently down for good and turn to the idea of a field. To replace the little ball, we need a new kind of thing, and the good news is that physics already had one sitting in plain sight, doing quiet work for nearly a century before anyone thought to build matter out of it. That thing is the field. Before we can understand a particle as a ripple, we have to be at home with the water it ripples in. You already know one field by feel, even if you have never named it that way. Hold two magnets near each other, and you feel a push, or a pull, across the empty gap between them. Nothing visible connects them, yet the force is real, and you can move your hands against it. That invisible influence filling the space around each magnet, reaching out to act on the other, is a field. A field is simply a quantity that has a value at every point in space. The magnetic field has a strength and a direction at every spot around the magnet, stronger near the poles, weaker far away, and that pattern of values spread through space is the field itself. The idea grew up in the 1800s, largely through Michael Faraday, a largely self-taught English experimenter of rare physical intuition, and James Clerk Maxwell, the Scottish theorist who turned Faraday's pictures into precise equations. Faraday, watching iron filings arrange themselves into curving lines around a magnet, became convinced that the space around magnets and charges was not empty, but filled with lines of force, a real physical influence reaching through it. Most physicists of the day prefer to think of forces leaping instantly across empty distance. Faraday's filling of space struck them as too homely, too unmathematical. He turned out to be right. Maxwell gave the fields their mathematics, and in doing so found something breathtaking. His equations for the electric and magnetic fields taken together allowed a wave, a ripple in the fields that could move on its own through empty space. When he calculated how fast that ripple would travel, the number came out equal to the measured speed of light. Light, Maxwell realized, is a wave in the electromagnetic field, an oscillation of electric and magnetic values rolling through space. Radio waves, visible light, X-rays, all of it is the same field, vibrating at different rates. The room you're in right now is full of this field, carrying every signal and every ray of light through it. Hold on to two features of a field, because they are exactly the features the little ball could never provide. First, a field is spread out. It is not at one point. It has a value everywhere at once, filling all the space it occupies. Second, a field can carry waves, ripples that move and spread and overlap and interfere. rising where two crests meet and cancelling where a crest meets a trough, spread out and able to interfere. These are precisely the wave-like behaviours we kept running into with the electron, the spreading through both slits, the bands of interference. So a field is a thing that is genuinely everywhere and that naturally supports waves. That already sounds closer to the strange electron than a tiny ball ever could. But there is a gap to cross. The electromagnetic field of Faraday and Maxwell is a smooth, continuous thing. Its waves can be as gentle or as strong as you like, any size at all. That is the classical field, and on its own it does not explain the lumps. Light, recall, does not arrive in any amount you please. It comes in photons, countable packets of fixed size. A smooth field has no packets in it. So the field, as Maxwell left it, is half the answer. It gives us something spread out that carries waves. What it lacks is the graininess, the countable lumps. The next step is to take this smooth field and find the rule that makes its energy come in packets, to quantize it. That step turns the field from a backdrop into the very stuff that particles are made of. Maxwell's field was smooth and continuous, able to carry waves of any size at all. But light does not come in any size. It comes in photons, fixed countable packets. To bridge that gap, physicists had to take the smooth field and find the rule that forces its energy into lumps. That step is called quantizing the field, and it gave birth to the deepest theory we have, quantum field theory. The work began in the late 1920s, soon after the basic quantum mechanics of single particles had settled. The leading minds turned to the electromagnetic field and asked a sharp question. What happens if we treat the field itself by the rules of the quantum world, the same way we had just learned to treat the electron? The answer reshaped everything. To get a feel for it, picture the field as something like a vast array of tiny springs filling all of space, each able to vibrate. In Maxwell's classical world, each spring could vibrate by any amount, gently or fiercely, with no restriction. Quantizing the field changes that. Now each spring can only hold energy in fixed steps, like a ladder with rungs and no in-between. A spring can have one rung of energy, or two, or three, but never 1.5. The steps are not optional. They are forced by the same quantum rule that made Planck's packets and Heisenberg's blur. And here is the move that turns a field into particles. Each rung of energy in the field is a photon. One rung climbed, one photon present. 2 rungs, 2 photons. The photon is not a separate little object flying through the field. It is a unit of excitation of the field, one quantum step up in the field's energy at some place. When you turn on a light, you're adding rungs to the electromagnetic field, exciting it, and each rung added is one more photon set loose. When that light is absorbed, the field steps back down, rung by rung, and the photons are gone. The packets of light that puzzled Planck and Einstein are simply the field's energy, counted in its smallest allowed steps. This was the great reframing carried forward by a group of brilliant young theorists, with the English physicist Paul Dirac among the first and boldest. Dirac, a famously silent and precise man, wrote a paper in 1927 that treated the electromagnetic field quantum mechanically and showed how photons emerge naturally from it. In that work, the photon stopped being an awkward guest, half wave and half particle, and became something cleaner. It was an excitation of a field, and the field was the fundamental thing. The wave nature and the particle nature were no longer in conflict. The field spreads and waves and interferes, which gives the wave behaviour, and its energy comes only in countable rungs, which gives the lumps. Both at once, with no contradiction, because they describe 2 true features of the same underlying field. Notice what this does to the old argument about whether light is a wave or a particle. The question dissolves. Light is neither a wave nor a particle in the old senses. It is a field, and a field naturally does both of the things we kept arguing over. It spreads like a wave because it is spread out everywhere, It comes in countable photons because its energy is quantized into steps. The long fight was a sign that we were forcing one underlying thing into two ill-fitting boxes. For light, this was a triumph. The photon had found its proper home as a ripple in the electromagnetic field. But it raised an immediate and thrilling possibility. If the photon is a ripple in a field, then what about the electron? Could the electron too be a ripple in some field of its own? To answer that, Dirac would have to write an equation for the electron that respected both the quantum world and Einstein's relativity, and that equation would deliver a shock no one saw coming. If the photon is a ripple in the electromagnetic field, the natural next thought is to ask whether the electron is a ripple in a field too. To get there, Paul Dirac set himself a hard technical task. He wanted an equation for the electron that obeyed both of the great theories of the new century at once, the quantum rules of the very small and Einstein's relativity of the very fast. The Schrödinger equation handled the quantum side but ignored relativity. Dirac wanted both, and in 1928 he found the equation that bears his name. The Dirac equation was a thing of startling beauty, and it worked better than he had any right to expect. Out of it, with no extra assumptions, came the electron spin, that built-in two-sidedness that Stern and Gerlach had found, and Goldschmidt and Uhlenbeck had named. Schrödinger had to add spin to his picture by hand. Dirac's equation produced it on its own, as a necessary consequence of combining quantum mechanics with relativity. That alone marked it as deep. The equation knew something the people who wrote it had not put in. But the equation came with a riddle, and Dirac was too honest to ignore it. When he solved it, the mathematics insisted on twice as many solutions as he expected. Half of them described the ordinary electron with its usual energy. The other half described something with negative energy, a state that seemed to make no physical sense. You cannot simply throw away half the solutions of an equation you trust. They were telling him something, and he had to work out what. His first attempt was clever and not quite right, but the spirit of it pointed the way. After some struggle, Dirac took the bold step of believing the equation rather than his expectations. The extra solutions he proposed described a new kind of particle, one with the same mass as the electron but the opposite electric charge. Where the electron is negative, this twin would be positive. It was a mirror-image electron predicted on the strength of mathematics alone, a particle no one had ever seen. This was one of the first times in physics that pure theory had insisted, ahead of any experiment, that a new piece of the world must exist. The waiting did not last long. In 1932, an American experimenter named Carl Anderson was studying cosmic rays, the steady rain of high-energy particles that falls on the Earth from space. He used a cloud chamber, a device in which a charged particle leaves a visible track of tiny droplets, and he placed it in a magnetic field so the tracks would curve, bending one way for a negative charge and the other way for a positive one. Among the tracks he found something with the mass of an electron but curving the wrong way, as if it carried a positive charge. He had found Dirac's mirror particle. It was named the positron, the positive electron, the first piece of antimatter ever seen. Sit with the order of events because it changed how physics understood itself. The particle was demanded by an equation before anyone looked for it. The mathematics, pushed to be consistent, predicted a whole category of matter that turned out to be really there. We now know that antimatter is general. Almost every kind of particle has an antiparticle, a twin with opposite charge. Bring a particle and its antiparticle together, and they annihilate, their mass converting entirely into energy, usually a burst of photons. The universe has a built-in mirror, and Dirac found its edge in a page of algebra. Antimatter matters here for a reason beyond its strangeness. The Dirac equation, by uniting quantum theory and relativity, was pushing physicists toward a picture in which the electron, like the photon, is best understood not as a thing, but as an excitation of a field that naturally allows both the particle and its mirror twin. That picture is the heart of everything to come, and it is time to say it plainly. We have gathered everything we need. We have a field that is spread through all of space and carries waves, and we have the quantum rule that forces a field's energy into countable lumps. Put them together and you reach the central idea of this whole story, the answer that replaces the little ball. A particle is one quantum of excitation in a field that fills all of space. Said more plainly, a particle is a ripple in a field. This chapter is the hinge the rest of the script turns on, so we'll say it carefully and let it settle. Begin with the photon, where the idea is cleanest. There is one electromagnetic field spread everywhere, filling this room and the space between the stars. When that field is at its lowest energy, undisturbed, there are no photons. Add one quantum of energy, excite the field by one rung at some place, and that single ripple is one photon. The photon is not a tiny ball of light flying along. It is the field, briefly raised by one step, the disturbance travelling as the field passes the excitation along. Light is the electromagnetic field, rippling. Now make the leap that quantum field theory makes. The electron works the same way. There is an electron field, spread through all of space, just as real and just as everywhere as the electromagnetic field, though we cannot feel it directly. When that field is undisturbed, there are no electrons. Add one quantum of excitation to it, and that single ripple is one electron. The electron is not a small solid speck. It is one quantized ripple in the electron field, a disturbance in a thing that fills the whole universe. Every electron in your body is a ripple in the same vast field, and that field is present even in the empty spaces between the ripples. This single idea answers, all at once, the failures that broke the little ball. Why does the electron spread through both slits and interfere with itself? Because it is a ripple in a field, and ripples spread and interfere by nature. Why does it still arrive as one countable dot? Because the field's energy comes only in whole rungs, and one rung is one electron, indivisible as a unit even while spread out as a wave. Why is it a wave and a particle at once? Because it was never either. It is an excitation of a field, and a field naturally does both, spreading like a wave and counting like a lump. The contradiction that haunted us was the sound of forcing a ripple into the shape of a ball. Hold the comparison gently and then test its edge, the way we have done all along. A particle is closer to a sound than to a stone. A sound is not a thing in itself. It is the air, disturbed in a pattern, moving along. You cannot hold a sound in your hand or cut it in half, yet it is perfectly real, and you can count beats and pitches. A particle is like that, a disturbance in a field rather than an object in its own right. But here the comparison reaches its edge, and the edge is the whole point. A sound in air can be any loudness at all, smoothly, with no smallest unit. A ripple in a quantum field cannot. Its energy comes only in whole steps, and one step is one particle. The graininess that a sound wave lacks is exactly what makes the quantum field's ripples countable, exactly what makes them particles rather than a smooth blur. So the smallest piece of anything is not a grain at all. It is a ripple, a single quantum of excitation in a field that fills everything, spread out like a wave and counted like a lump, because that is simply what a quantized field allows. The little ball is gone, and in its place is something stranger, and once you see it, far more satisfying. And this new picture immediately explains a fact so familiar we never thought to wonder at it. Every electron in the universe is exactly the same. Here is a fact so ordinary that almost no one stops to find it strange. Every electron in the universe is exactly, perfectly identical. The electron in your fingertip and an electron at the centre of a distant star have precisely the same mass, the same charge, the same spin, down to the last decimal place anyone can measure. Not similar, not nearly the same, identical, with no detectable difference of any kind. Once you notice this, it should astonish you, and the field picture explains it in a single stroke. Think about how unusual perfect sameness is among ordinary objects. No two grains of sand are truly identical. No two marbles, no two ball bearings off the same machine are exactly alike if you measure finely enough. Each has its own tiny scratches, its own slightly different mass, its own small flaws. Anything manufactured as a separate little object carries its own history, and history leaves differences. If electrons were tiny balls, each made somehow as its own object, you would expect the same. Slight variations, a spread of masses however small, a little individuality. Instead, there is none at all. Every electron is a flawless copy of every other. The field picture makes this not just possible but inevitable. There is one electron field, a single field filling all of space. Every electron is a ripple in that one field. They are all the same kind of thing because they are all excitations of the very same underlying field, the way every wave on one ocean is a disturbance of the same water. Two waves on the sea can differ in height and position and motion, but they are made of the same water, obeying the same rules, and in that deeper sense they are the same kind of disturbance. Electrons are like that, except even more so, because the rungs of a quantum field are all exactly equal in size. One quantum of the electron field is identical to any other quantum of the electron field necessarily, because the field allows only that one size of step. This is why an electron has no individuality and no history written into it. It is not a manufactured object that came off a line at some moment and accumulated where. It is a ripple, and a ripple has no maker's marks. When an electron is created, the field is simply excited by one rung. When an electron is destroyed, the field steps down by one rung. The same field can lose a ripple here and gain one there, and nothing is missing, because no particular electron was ever a distinct object to begin with. They are interchangeable in the deepest way, copies that are not even copies, because there is no original. The physicist Richard Feynman once relayed a playful idea along these lines, told to him by his teacher John Wheeler. Perhaps all electrons are identical because there is in some sense only one electron, weaving back and forth through time and showing up everywhere at once. The idea is not taken literally as the explanation, and it has its problems, but it points at the right feeling. The sameness is so total that it begs for a single shared source. Quantum field theory gives that source plainly. The shared source is the field. Not one electron threading all of space, but one field across all of space, rippling in identical units. This identity is not a curiosity off to the side. It runs through everything. The exact sameness of electrons is part of why the Pauli exclusion principle works so cleanly, why atoms of the same element behave alike everywhere in the universe, why chemistry is reliable on Earth and in galaxies we will never visit. The world is lawful and repeatable, in part because its building blocks are not individual objects but identical ripples in shared fields. And that phrase, the field even where there are no ripples, points at the next strange place we have to go. If the field is there whether or not it's excited, what is happening in the field when no particles are present at all? We have said several times now that the field is there even where there are no particles, the way the ocean is there whether or not a wave is crossing it. It is time to take that phrase seriously and ask what it really means, because it leads to one of the strangest and most thoroughly tested ideas in all of physics. What is happening in a field where nothing is? What does true emptiness actually contain? Start with the picture we have built. A particle is a ripple in a field. No ripple, no particle. So you might think that a region of space with no particles in it is a region where the field is simply flat and still, sitting quietly at zero, doing nothing. That is the natural guess, and it is the picture most people carry of empty space. Take a box, remove every particle of matter, every photon of light, cool it toward the lowest temperature there is, and you would seem to have nothing. A perfect vacuum. The field present, but motionless. A calm, undisturbed sheet. Hold that picture. Honour it. Because it is the sensible classical expectation. And then watch the quantum world refuse it. The reason it cannot be true is one we have already met. The uncertainty principle. Recall that the principle forbids certain pairs of quantities from both being perfectly sharp at once. For a field, It turns out that the strength of the field at a point and the rate at which that strength is changing are just such a pair. They cannot both be exactly zero at the same time, for the same reason an electron cannot have both a sharp position and a sharp motion. A field that sat perfectly flat and perfectly still would violate the uncertainty principle. The quantum world does not allow that much stillness. So the field in empty space cannot be flat and motionless. It must always carry a residual trembling, a faint unavoidable jitter, even at its lowest possible energy, even with every particle removed and the temperature taken as low as it can go. This lowest energy state of a field, the quietest it is allowed to be, is called the vacuum state. And the crucial word is that the vacuum is the quietest state, not a silent one. There is a floor of motion below which the field cannot go, a permanent restlessness built into empty space itself. This changes the meaning of the word vacuum completely. We tend to use empty and nothing as the same word, a region with nothing in it and nothing happening. The quantum vacuum is not that. It is the state with no particles, no ripples that count as real, settled excitations, and yet it is not still and not empty in the deeper sense. The fields are there, filling it, and they are forever trembling at their lowest allowed level. Empty space is not an inert stage on which physics happens. It is a humming, restless medium, and that hum is the baseline of reality, present everywhere, in this room and in the deepest void between galaxies. It would be fair to be skeptical here. This sounds like the kind of claim that is easy to state and impossible to check, a story told about a place where, by definition, there is nothing to see. If that trembling were truly beyond all detection, we would be right to treat it with caution, and physicists were cautious at first. But the restless vacuum is not a story that hides safely out of reach. It pushes on the world in ways we can measure, with real instruments, to real precision. Empty space, it turns out, has effects. The next steps are about catching those effects in the act, starting with the energy that even nothing is forced to carry. We ended on a promise to take the trembling of empty space seriously, and the first thing to take seriously is that it carries energy. To see why, go back to the picture of the field as a vast array of tiny springs filling space, each one able to vibrate. Quantum mechanics has a firm rule about springs, and it is worth meeting on its own before we apply it to the field. Take a single quantum spring, an oscillator, and try to bring it completely to rest. In the old physics you could. A pendulum can hang straight down, perfectly still, with zero energy of motion. The quantum world forbids this. A spring at perfect rest would have both a sharp position, sitting exactly at the bottom, and a sharp motion, exactly zero, and the uncertainty principle does not allow both at once. So the quantum spring can never fully stop. Even in its lowest possible state, it keeps a small residual quiver, a minimum energy it cannot shed. This leftover is called zero-point energy, the energy that remains when all other energy has been removed. Now remember that a field is like countless such springs, one for every way it can vibrate, every wavelength and direction, packed through all of space. Each of those modes carries its own small zero-point energy that it can never give up. Add them together across all the modes filling a region, and the empty vacuum is left holding a background of energy, the summed quiver of every mode of every field, present even when not a single real particle is there. The hint of this went back as far as 1912, when Max Planck, revising his work on radiation, found a stubborn leftover term that would not go to zero. This is a strange and humbling place for the calm to hold. The vacuum is not the absence of energy. It is the lowest energy a region can have, and that floor is not at zero. Empty space hums with a baseline of zero-point energy that belongs to the fields themselves, woven in by the same uncertainty rule that smears the electron and forbids perfect stillness anywhere in the quantum world. It would be easy to oversell this, so let us be careful about what it does and does not mean. The zero-point energy is real, but because it is the lowest state the same everywhere, you cannot draw on it the way you draw on a battery. There is no lower level to fall to, so in ordinary circumstances it simply sits there as the unmovable floor of reality, doing nothing you can extract. It is the baseline against which everything else is measured, and a baseline by itself drives nothing. There is one place where this background energy becomes a genuine and serious puzzle, and honesty requires naming it even though its full reckoning comes later. When physicists try to add up the zero-point energy of all the fields and ask how much it should weigh, how strongly it should bend the universe through gravity, the calculated number comes out staggeringly larger than what the universe actually shows, by a margin so vast it is among the worst mismatches between theory and observation in all of science. The trembling is real, and its small effects are measured exactly, as we are about to see. Yet its total weight remains a deep unsolved problem. We hold both facts calmly and side by side. For now, set the grand puzzle down and keep the solid part. Empty space has a lowest energy that is not zero, a permanent quiver of every field. From this restless baseline comes a whole family of effects, and the first one we meet is a familiar character in disguise. People often describe the vacuum's activity as a froth of particles flickering in and out of existence, and that phrase deserves a chapter of its own, because it is both useful and, taken too literally, quietly misleading. You will often hear the quantum vacuum described in a vivid way. Empty space, people say, is boiling with virtual particles, pairs of particles and antiparticles that flicker into being and vanish again, borrowing energy for the briefest instant before paying it back. It is a striking image, and it appears in serious books and lectures, so it deserves a careful and honest look. Some of it is genuinely useful. Some of it, taken literally, can quietly mislead, and the calm thing to do is to separate the two. The phrase grows out of a real tool. When physicists calculate how particles interact, say two electrons repelling each other, they use a method built by Richard Feynman, the famous diagrams that carry his name. In a Feynman diagram, two electrons approach, and between them runs an internal line, often drawn as a photon passed from one to the other, carrying the force. There can be more elaborate versions with extra internal lines that loop and branch, including lines that look like particle-antiparticle pairs appearing and disappearing inside the diagram. These internal lines are called virtual particles. They are the parts of the picture that live entirely inside the interaction, never entering or leaving as real, detectable particles. Here is the honest heart of it. A virtual particle is not a little object that briefly exists. It is a term in a calculation. Each Feynman diagram is one piece of a long sum, a careful bookkeeping of all the ways an interaction can proceed, and the internal lines are names for the mathematical pieces of that sum. They are extraordinarily useful because the diagrams make a fearsome calculation visual and manageable, and they give the right answers to astonishing precision. But the lines inside the diagram do not correspond to particles you could ever catch in a detector. They are not events happening in space so much as steps in arithmetic. So the froth of particles flickering in and out is best understood as a way of talking, a picture laid over the mathematics, not a literal description of empty space. What is really there is the restless vacuum we already met, the fields trembling at their zero-point energy. That trembling is genuine. When we calculate its effects, the math is organized into diagrams, and the diagrams contain virtual lines, and it is tempting to read those lines back into reality as tiny, short-lived particles. That last step is the one to resist. The fields are real and always present. The virtual particles are the language we use to compute what those fields do. Why insist on the distinction when the vivid version is so memorable? Because the whole point of this story is to say what things really are, and a particle, real or virtual, is not the right bottom layer. The field is. Real particles are the fields countable, lasting excitations, the ones that travel and trigger detectors. Virtual particles are not lesser versions of those. They are not excitations at all. They are pieces of a sum describing how the fields nudge one another. Keeping that straight is part of keeping the wonder honest rather than spooky. None of this makes the vacuum's effects any less real. That is the remarkable part. The trembling of the fields computed through these diagrams with their virtual lines predicts specific, measurable things about the world, forces and shifts you can put an instrument on. The bookkeeping may be abstract, but its results show up on dials. The clearest first example is a gentle push, a force that appears between two ordinary metal plates placed close together in a vacuum, with nothing between them at all but the trembling of empty space. In 1948, a Dutch physicist named Hendrik Casimir, working at the Philips Research Laboratory, made a quiet and daring prediction. Take two flat metal plates, ordinary uncharged conductors, and place them very close together, facing each other, in a perfect vacuum. He calculated that they should feel a faint attraction, pulled gently toward each other by nothing but the structure of empty space between them. No charge, no magnetism, no known force of the usual kind, just the vacuum, pushing. The reasoning rests on everything we have built. Empty space is full of the electromagnetic field, trembling at its zero-point energy, with vibrations of every wavelength present in its restless baseline. Now slide two metal plates close together. Metal constrains the electromagnetic field at its surface, and that constraint means only certain wavelengths can fit neatly in the gap between the plates, the ones that match the spacing, the way a guitar string of fixed length can only sound certain notes. Outside the plates, in the open space around them, no such restriction applies, and vibrations of every wavelength crowd in freely. So there are more modes of the trembling field outside the gap than inside it. The vacuum is, in a precise sense, slightly less full of field vibration between the plates than outside them. That imbalance produces a pressure difference, a tiny net push from the richer outside against the sparser inside, and the plates nudge toward each other. The force comes from the difference in the zero-point energy of the field, reshaped by the mere presence of the two plates. Empty space, given a boundary, pushes. The force is real but exquisitely small, and it grows quickly as the plates get closer, fading to nothing as they move apart. For plates a hair's width apart, it is so faint that measuring it cleanly took decades of patience, because any speck of charge, any trace of magnetism, any warmth or vibration could swamp so delicate a pull. Casimir had given a clear prediction, with a definite size set by the spacing and by Planck's constant, but turning that prediction into a clean measurement was a long, careful labour. The confirmation came near the end of the century. In 1997, the physicist Steve Lamoureux, then in the United States, measured the Casimir force to good accuracy and found it matched Casimir's prediction. Soon after, other experimenters, including Umar Mohideen, working with a fine sphere brought close to a surface to sidestep the difficulty of keeping two plates perfectly parallel, measured it more precisely still. The numbers agreed with a calculation whose only real ingredient was the zero-point trembling of the electromagnetic field. Empty space had been weighed against a theory, and the theory held. It is worth pausing on how strange and how solid this is at once. Two plain metal plates carrying no charge are drawn together across a vacuum by a force that exists only because the field between them is slightly quieter than the field around them. There is nothing there, in the everyday sense, no stuff in the gap, and yet there is a measurable pull, and its size was predicted in advance from the structure of nothing. The restless vacuum is not a metaphor. It is a thing with consequences you can put a number on and check. The Casimir push proved that the vacuum has effects on objects placed within it, but there was an even sharper test waiting, one that reached the electron directly. If empty space truly trembles, then an electron sitting in it should feel that trembling, should be jostled by the restless field around it, and that jostling should shift its behaviour by a tiny calculable amount. Catching that shift, in a single atom of hydrogen, gave the field picture its first hard quantitative proof. The Casimir push showed the vacuum acting on metal plates. The deeper test was whether the trembling of empty space could be caught acting on a single electron, inside a single atom, changing something we could measure with great precision. That test came in 1947, just before the Casimir prediction, and it is often counted as the moment quantum field theory had to grow up and start giving exact numbers. This setting was the hydrogen atom, the simplest there is, one electron bound to one proton. Dirac's equation, the beautiful one that had predicted antimatter, also predicted the energy levels of hydrogen, the specific rungs the electron can occupy. In particular, Dirac's theory said that two certain states of the hydrogen electron should have exactly the same energy, sitting at precisely the same level, indistinguishable in energy. For years, there was no way to check this finely enough to know whether it was truly exact. The means to check it came out of the Second World War. Radar research had pushed the technology of microwaves forward enormously, and physicists came out of the war with new tools for probing atoms with finely tuned radiation. In 1947, an American physicist named Willis Lamb, working with his student Robert Rutherford, used these microwave techniques to measure the hydrogen levels with unprecedented sharpness. They found that the two states Dirac said should match did not match. One was nudged very slightly above the other, by a tiny but unmistakable amount. This small gap is the Lamb shift. A tiny discrepancy in one atom might sound like a footnote, but it landed like a thunderclap because Dirac's theory was supposed to be exact and it was plainly, if barely, wrong. Something was nudging the electron that Dirac's equation did not include. The thing doing the nudging was the vacuum. The electron in the hydrogen atom is not sitting in true emptiness. It is sitting in the restless electromagnetic field, trembling at its zero-point energy, and that trembling jostles the electron constantly, smearing its position by a minute amount and shifting its energy in the two states by slightly different degrees. The vacuum reached into the atom and moved the rungs. The first person to show that this picture gave the right number was Hans Bethe, and the story of it has become famous for its plainness. Returning by train from a conference in 1947, Bethe did a rough calculation of how much the trembling vacuum should shift the electron's energy, and got an answer close to what Lamb had measured. It was an approximate calculation, and it sidestepped some deep difficulties that still had to be faced, but it pointed unmistakably at the cause. The shift was the vacuum acting on the electron, and the size came out right. This was the first hard, quantitative proof that the restless vacuum is real and that it touches matter measurably. The Casimir force, confirmed later, showed the vacuum pushing on plates. The Lamb shift showed the vacuum reaching inside an atom and moving an electron's energy by an amount we could measure and eventually calculate to many decimals. Empty space was no longer a passive stage. It was an active participant in the structure of every atom. But Bethe's quick calculation had stepped over a serious problem, one that haunted the whole theory. When physicists tried to compute these vacuum effects fully and exactly, the equations did not give small, sensible numbers. They gave infinity. The interaction of the electron with the trembling field, taken at face value, blew up without limit, predicting nonsense. Before the field picture could deliver its triumphs, that infinity had to be tamed, and taming it took some of the finest minds of the century. The infinities were not a minor nuisance. They threatened to sink the whole theory. When physicists tried to calculate exactly and completely how an electron interacts with the trembling electromagnetic field around it, the sums ran away to infinity. Ask for the electron's energy from these interactions, and the equations answered with a quantity beyond all bound. A theory that predicts infinity for a measurable thing is, on its face, simply broken. For a while in the 1930s and 40s, this looked like it might be the end of the field picture. The trouble can be felt without the mathematics. An electron is surrounded by the field it interacts with, and that interaction reaches across all distances and all wavelengths, including arbitrarily small distances and arbitrarily short wavelengths. When you add up the contribution from finer and finer scales, the pieces do not settle down. They keep growing, and the total has no limit. The closer you look, the more the interaction seems to contribute, without end. The electron, dressed in its own field, appeared to have infinite energy and infinite mass, which is plainly not what the scale reads. The escape was a set of ideas gathered under the name renormalization, and it came together around 1947 to 49 in the hands of a few remarkable people working largely in parallel. In the United States there was Julian Schwinger, a prodigy of dazzling formal power, who built the theory in dense and elegant mathematics. There was Richard Feynman, who approached the same problem through his diagrams and a physical intuition so strong it sometimes outran the proofs. And in Japan, working in the wreckage of a country devastated by war, with poor resources and cut off from much of the world, there was Shinichiro Tomonaga, who had reached many of the same results independently and earlier than the West realized. The core idea of renormalization is subtle, and once seen, almost reasonable. The infinities, it turns out, attach to a few specific quantities, chiefly the electron's mass and its charge. But we never measure the bare electron alone, stripped of its field. We only ever measure the real electron, the one already dressed in its interactions with the vacuum. So the trick is to stop pretending we know the bare values and instead fold the infinities into them, absorbing the runaway pieces into the mass and charge we measure in the laboratory. Once you express every prediction in terms of the measured mass and charge rather than the bare ones, the infinities cancel and what remains is finite, definite, and testable. The infinite parts were, in a sense, never observable on their own. They hid inside quantities we'd been measuring all along. This troubled some of its own inventors. Paul Dirac, for one, never made peace with renormalization, regarding the procedure of absorbing infinities as an ugly trick rather than a true understanding, a sign that something deeper was still missing. The discomfort was honest and is worth keeping. Renormalization works superbly, but the feeling that it papers over a gap has never fully gone away. The man who showed that these different approaches were one was Freeman Dyson, a young English physicist who in 1949 proved that Schwinger's formal method, Tomonaga's, and Feynman's diagrams were all the same theory wearing different clothes. Dyson stitched the strands into a single coherent quantum electrodynamics. For the breakthrough, Schwinger, Feynman, and Tomonaga shared the Nobel Prize years later, in 1965, with Dyson's unifying role widely honoured, even though the prize committee could name only 3. With the infinities tamed, quantum electrodynamics became the most precisely tested theory ever built. And the sharpest test of all involved a single number, the strength of the electron's own magnetism, predicted and measured to a precision that still has the power to stagger anyone who stops to take it in. Quantum electrodynamics, once renormalized, could finally make exact predictions, and one number above all became the proving ground. It is the strength of the electron's magnetism, often called its magnetic moment. The electron, as we saw with Stern and Gerlach, behaves like a tiny magnet. The question is exactly how strong that magnet is, and the answer is where theory and experiment meet more closely than anywhere else in all of science. Dirac's equation made a clean first prediction. It said the electron's magnetism should have a particular strength, captured by a number physicists write as G, and Dirac's theory gave G exactly equal to 2. This was already a triumph, a precise value falling straight out of the equation. For a while it seemed that might be the whole story, a tidy round number. But the trembling vacuum had something to add. The electron is never alone. It sits in the restless electromagnetic field, constantly interacting with it, and those interactions slightly change its magnetism. The real measured strength is not exactly 2. It is a little more, nudged upward by the electron's endless conversation with the vacuum around it. The first piece of that correction was calculated by Julian Schwinger, and it was so important to him that the formula is said to have been carved on his gravestone. His result added a small, specific amount to the Dirac value, and when it was checked, it matched. The vacuum's fingerprint on the electron's magnetism was there, and it was the size the theory said. From there, it became a contest of patience and precision on both sides. Theorists computed further corrections, ever smaller refinements, each one requiring more and more Feynman diagrams, more terms in the long sum, calculations so vast that they now stretch over years and fill volumes and lean on the largest computers. Experimenters, meanwhile, trapped single electrons and measured their magnetism with growing care, refining the number digit by hard-won digit. The two efforts raced each other deeper and deeper into the decimal places. The agreement they reached is hard to put in ordinary words, so reach for a comparison. Theory and experiment for the electron's magnetism now agree to about 12 places past the start of the number. To feel what that means, imagine measuring the distance from one coast of a continent to the other and having two completely independent methods agree down to less than the width of a single human hair. That is the kind of precision at play. A number computed from the trembling of empty space, term by painstaking term, matches a number read off a trapped electron to a part in a trillion or so. It is routinely called the most precise agreement between theory and measurement that human beings have ever achieved. Stand back and see what this precision is really telling us. The quantity being predicted is the magnetism of the electron, and the prediction is built entirely on the picture we have been assembling. The electron is an excitation of a field. It is surrounded by other fields trembling at their 0-point energy. Those fields nudge its magnetism by tiny amounts, calculated through the diagrams, the very same vacuum that pushed the Casimir plates and shifted the Lamb levels. That this whole edifice produces a number-matching reality to 12 decimal places is the strongest evidence we have that the field picture is not a story, but a true account of what the electron is. A theory this exact, for the electron and its field, naturally raised an ambition. If electrons and photons are ripples in fields, then perhaps everything is. Perhaps every particle in nature, every piece of matter and every force is an excitation of some field, and the whole list of nature's ingredients is really a list of fields. That ambition became the standard model. The success of quantum electrodynamics carried an obvious invitation. If the electron is a ripple in an electron field, and the photon a ripple in the electromagnetic field, then perhaps every particle in nature is the same kind of thing, a quantum of some field. Through the 1960s and 70s, physicists built exactly that, a catalogue of the fundamental fields whose ripples make up everything we have ever detected. It is called the Standard Model of Particle Physics, and at its heart it is a list of fields. The matter you're made of comes from two families of fields. One family is the quarks, which come in 6 kinds with playful names: up and down, charm and strange, top and bottom. Up and down quarks are the ones that matter for ordinary matter, because they combine to form the protons and neutrons in every atomic nucleus. The other family is the leptons, which includes the electron we have followed so closely, along with 2 heavier cousins called the muon and the tau, and 3 light ghostly particles called neutrinos. Each of these, every quark and every lepton, is the ripple of its own field, spread through all of space. 12 matter fields, and their ripples are the particles of substance. Then there are the fields whose ripples carry the forces, the messengers that let matter interact. The photon, the ripple of the electromagnetic field, carries the electromagnetic force, the push and pull between charges. The strong force, which binds quarks together inside protons and neutrons, is carried by particles called gluons, ripples in their own fields, named for the way they glue matter's smallest pieces together. The weak force, responsible for certain kinds of radioactive decay and for the reactions that make the sun shine, is carried by heavy particles called the W and Z bosons. Each force, in this picture, is a field, and each messenger is a ripple in it. This was not built in a day or by one person. The unification of the electromagnetic and weak forces into a single framework came through the work of physicists, including Sheldon Glashow, Steven Weinberg, and Abdus Salam in the 1960s. The theory of the strong force and quarks took shape over the same era and the years just after. Piece by piece, a sprawling zoo of particles that had been discovered in cosmic rays and accelerators, was organised into a clean underlying scheme. Not dozens of unrelated objects, but the ripples of a modest number of fields. The power of the standard model is hard to overstate. It accounts for nearly every particle and every interaction we have ever measured in the laboratory, often to remarkable precision, the same kind of precision we saw in the electron's magnetism. It is one of the most successful theories in the history of science, and its core message is the one this whole story has been building toward. The fundamental ingredients of the world are not little balls of different kinds. They are fields, a definite list of them, and the particles are their ripples. Reality at bottom is a set of fields filling all of space, each humming at its 0-point baseline, each able to be excited into the countable lumps we call particles. Yet the standard model left two great gaps that this part of the story must face. One is that the picture so far does not explain why the matter particles have the masses they do, why an electron is light and a top quark heavy. The other concerns those quarks themselves, the constituents of every proton and neutron, which behave in a way stranger than anything yet, because no matter how hard you try, you can never pull a single quark out and hold it alone. The quarks make up the protons and neutrons in every nucleus, and they are the constituents of nearly all the matter you can touch. But they hold a secret that sets them apart from every particle we have met so far. You cannot get one by itself. No experiment has ever isolated a single free quark, and the reason is not a failure of effort. It is built into the force that binds them. To understand the deepest layer of ordinary matter, we have to understand why its pieces refuse to come out alone. The story of quarks begins as a piece of pattern finding. In 1964, two physicists, Murray Gell-Mann and independently George Zweig, noticed that the bewildering crowd of particles streaming out of accelerators fell into neat patterns if you suppose they were built from a few smaller pieces. Gell-Mann named these pieces quarks, taking the odd word from a line in a James Joyce novel. At first, it was unclear whether quarks were real objects or just convenient bookkeeping for the patterns. They had strange properties, including electric charges that were fractions of the electron's charge, something never seen in a free particle, and no one had ever detected one. The evidence that quarks are real, and really inside the proton, came at the end of that decade from an experiment in the spirit of Rutherford's. At the Stanford Linear Accelerator in California, physicists fired electrons of very high energy straight into protons and watched how they scattered. This is called deep inelastic scattering. Deep because the electrons probe deep inside the proton. Just as Rutherford's alpha particles had occasionally bounced back hard and revealed the tiny nucleus, these electrons sometimes scattered sharply, as if they had struck small, hard, point-like objects inside the proton. The work of Jerome Friedman, Henry Kendall, and Richard Taylor showed that the proton is not a smooth blob. It has hard little pieces inside, and those pieces match the quarks, so quarks are real, and they sit inside every proton and neutron. But now comes the strangeness. The force that binds quarks, the strong force carried by gluons, behaves unlike any force in everyday life. With gravity or electric force, the pull weakens as things move apart. The strong force does the opposite. As you try to pull two quarks apart, the force between them does not fade. It stays strong, even grows, as if they were joined by an elastic band that pulls harder the more you stretch it. Follow that band to its conclusion. As you pull a quark away from its partners, you pour energy into the stretching bond, and the energy stored climbs and climbs. Long before the quark can come free, the energy in the bond becomes so great that it is enough, by the conversion of energy into matter, to create a brand new quark and antiquark pair out of the vacuum. The band snaps, and at the snapped ends sit the new particles. Instead of one free quark, you now have new pairs, each bound up again. Pull as hard as you like, and all you ever produce is more bound groups, never a lone quark. This is called confinement, and it means a single quark is never seen alone. This is a fitting deepening of our whole theme. Even the constituents of the proton are excitations of fields, quark fields and gluon fields, and the field picture explains why they stay bound, because the strong field's energy grows with stretching until it makes new ripples rather than releasing old ones. The quark is real, countable inside the proton, and yet permanently uncatchable on its own. And the same standard model that holds the quarks also holds the answer to a question we set aside, the origin of mass itself, in a field that fills all of space like an unseen ocean. We have been treating mass as something a particle simply has, a given number, the electron light and the top quark heavy. But in the field picture, mass is not a built-in lump of stuff. It is something most particles acquire by interacting with yet another field, one that fills all of space and never switches off. This is the Higgs field, and the story of how it gives weight to the world and how it was finally caught is among the great achievements of recent physics. The idea took shape in 1964 in the work of several physicists at once, among them Peter Higgs, whose name became attached to it, along with François Englert and Robert Brute, and others who reached related conclusions independently. They were wrestling with a problem in the equations of the forces. The mathematics worked beautifully if the fundamental particles had no mass at all, but the particles plainly do have mass. The proposed resolution was bold. Perhaps the particles are massless in themselves, and they gain their mass by moving through a field that pervades all of space, dragging on them as they go. The Higgs field is unusual in a crucial way. Most fields rest at zero in the vacuum, trembling only at their 0-point baseline, with no particles present. The Higgs field is different. Its lowest energy state is not at zero, but at some steady non-zero value, the same everywhere, filling the universe like an unseen ocean that has no surface and no shore. Every particle that feels this field moves through it always, and that constant interaction is what we experience as the particle having mass. A particle that interacts strongly with the Higgs field is hard to push, slow to change its motion, which is exactly what it means to be heavy. A particle that ignores the field, like the photon, stays massless and flies at the speed of light. Reach for the ocean comparison and then find its edge, as we always do. You can picture mass as a kind of drag, particles wading through the Higgs ocean, the heavy ones ploughing through thick resistance, the light ones slipping easily. The picture helps, but it has a limit that matters. Real drag slows a moving thing down and eventually stops it, draining its motion. The Higgs field does not slow particles to a halt or steal their energy that way. It gives them the property of mass, their resistance to being accelerated, while letting them coast freely once moving. The ocean gives weight, but it is not a thick syrup that brings everything to rest. The comparison carries you part way and then must be set down. For decades, the Higgs field was a beautiful idea with no direct proof. The way to test it followed everything we have learned. If the Higgs is a field, then like any field, it should have a ripple of its own, a particle, the Higgs boson. Find that particle, and you confirm the field is really there. But the Higgs boson is heavy and hard to make, requiring collisions of enormous energy to stir the field strongly enough to shake one loose. That energy was reached at the Large Hadron Collider, the vast machine at CERN near Geneva, where protons are smashed together at tremendous speed. On the 4th of July 2012, two great experiments there, called ATLAS and CMS, announced that they had found a new particle with just the properties expected of the Higgs boson. The field that gives mass to the world had finally been confirmed by catching its ripple. The last major piece of the standard model was in place, and with it the picture was nearly complete. Everything, even mass itself, comes back to fields. We have built the case carefully, chapter by chapter, and reached a clear claim. The fundamental things are fields, and particles are their ripples. Now it is worth turning to face the most direct objection, the one a thoughtful skeptic would raise. We keep saying there are no little balls, only fields. But every detector in every laboratory registers particles. It clicks. It records a dot, a track, a discrete arrival. If there are only fields, why does the world insist on showing us particles? This chapter sits with that question honestly. Think about what a particle detector actually does, whether it is the cloud chamber that revealed the positron or the great machines at CERN. The detector does not show you a spread out wave. It gives you discrete countable events. A flash here, a click there, a single track curving through. When an electron arrives at a screen, it lands at one point, one dot, exactly as it did in the double-slit experiment. The evidence of our instruments is stubbornly grainy. It is, on its face, the most particle-like thing imaginable, and it is what makes the little ball so hard to give up. The field picture answers this without flinching, and the answer is the quiet heart of the whole modern view. The field is the real and continuous thing present everywhere, spread out. But the field's energy is quantized, allowed only in whole rungs, as we established long ago. So when a field deposits energy into a detector, it cannot deposit a smooth smear. It must deliver its energy in a whole quantum, one rung at a time, at one place. The click is the field handing over one indivisible unit of energy to the atoms of the detector. The dot on the screen is where one quantum of the field's energy was absorbed. The particle-like event is real, but it is the signature of a quantized field interacting, not the arrival of a tiny ball. So the graininess we see is the graininess of the field's energy, not the graininess of little objects flying through space. Between being emitted and being detected, the thing travels as a spread-out field excitation, passing through both slits, interfering with itself, behaving as no ball could. Only in the act of interaction, of depositing its energy, does it present a single localized event, because the energy comes in one lump. The detector does not reveal a particle that was there all along. It marks the moment a field's ripple gave up one quantum of energy at one spot. A number of physicists have argued on exactly these grounds that the honest thing is to say there are only fields, and that the word particle is a name for how a quantized field shows up in a measurement. In this view, the particle is not a fundamental object at all, but an event, a happening, the discrete way a continuous field interacts. What exists is the field. What we call a particle is what the field does when it transfers a whole quantum of itself to something else, like a detector or another field. This reframing is more than a matter of taste, because it dissolves the last hold of the little ball. The clicks were the strongest argument that particles are real objects, and the field picture shows the clicks are exactly what a quantized field must produce, with no little object required. The wave behavior and the countable clicks both come from one source, a field whose energy is granular. And once you take seriously that the field is what is real, you find that the very idea of how many particles are present, which seemed so solid, starts to soften in ways that go deeper still, beginning with a result that says a particle can never be perfectly pinned to a place at all. If the particle is really an excitation of a field, then some things we took for granted about particles should turn out to be approximations, true enough in ordinary life but not exact. One of those is the simple idea that a particle can be located, that it sits in a definite region you could draw a box around. We already know from the uncertainty principle that position and motion cannot both be sharp. But the field picture, taken with relativity, says something stronger and stranger. A particle can never be perfectly localized at all, not even in principle, not even setting motion aside. This is a subtle result, and it deserves a calm and careful telling rather than a dramatic one. In the simpler quantum mechanics of Schrödinger, you can at least imagine a particle whose wave function is squeezed into a tiny region, sharply present here and nowhere else, even if its motion then becomes wild. But when you combine quantum theory with relativity, as quantum field theory must, that picture breaks down. The mathematics shows that you cannot build a state that is a single particle, confined entirely within a finite region of space, with strictly nothing outside. Any attempt to perfectly localize a particle smears it, in a precise technical sense, across all of space, however faintly. There are several deep theorems pointing this way, worked out over the second half of the 20th century, and physicists give them careful names. The upshot, stated plainly, is that perfect localization is impossible for a relativistic quantum particle. A particle is not the kind of thing that can be exactly here and exactly not there. The closest you can come is a state concentrated mostly in one region, with an unavoidable faint presence reaching beyond it. The sharp little object sitting cleanly at one address is not just unknown to us. It does not exist as a consistent possibility within the theory. Why does this happen? The reason traces back to the field and its energy. To confine a field excitation into a smaller and smaller region, you have to involve higher and higher energies. The same way, squeezing a wave into a tighter space demands shorter wavelengths and thus more energy. Push hard enough toward perfect localization, and the energies involved become large enough to create new particles out of the vacuum, the same effect we saw with the quarks. The attempt to pin one particle into a point ends up stirring the field into making more particles. The very notion of a single, perfectly placed particle defeats itself. This is another quiet confirmation that the field is the truer object, and the particle is a derived, approximate notion. A field has no trouble being everywhere at once, because that is its nature. It is the particle, the countable ripple, that we keep trying and failing to treat as a small localized thing. Every time we press the particle to behave like a tiny ball with a definite address, the field underneath reasserts itself, refusing to be cut into perfectly placed pieces. The particle is real as a count, real as a quantum of energy, but not real as a point you can isolate. So the little ball loses even its last refuge, the idea that at least, deep down, it has a definite location waiting to be found. It does not. And there is a still more startling consequence waiting once we let go of the particle as fundamental. If particles are not basic objects but features of fields, then even the simple act of counting them, asking how many particles are in a region, may not have one fixed answer. It may depend on who is asking, and on how they are moving. We have let go of the particle as a perfectly placed object. There is one more piece of its old solidity to surrender, and it is the strangest yet. The number of particles in a region, which sounds like the most definite fact imaginable, turns out not to be absolute. Two observers, looking at the very same region of space, can disagree about how many particles are there, and both can be right. The count depends on how the observer is moving. This is the Unruh effect, and it follows from taking the field as fundamental. The result came in 1976 from the physicist William Unruh, building on related work by others including Stephen Hawking, whose black hole result we will meet next. Unruh asked a clean question. Take a region of empty space, the quantum vacuum, with no particles in it as judged by an observer floating freely, drifting without acceleration. Now consider a second observer moving through the same region, but accelerating hard, speeding up steadily. What does the accelerating observer see? The astonishing answer is that the accelerating observer does not see empty space. They see a warm bath of particles, a faint glow, where the floating observer sees nothing at all. This is not a trick of perception or a mistake by one of them. It is built into how fields and observers relate. The vacuum, the lowest energy state with no particles, is defined with respect to a particular way of moving through it. For the freely floating observer, the field is in its quiet ground state, no ripples that count as particles. For the accelerating observer, the same field state viewed from their accelerating frame appears full of thermal particles, a real bath with a definite temperature set by how hard they are accelerating. The faster the acceleration, the warmer the bath. The particle count is not a property of the region alone, it is a relationship between the field and the observer's motion. Sit with how deep this cuts. We tend to think that whether a particle exists is a plain yes or no fact about the world, the same for everyone. The Unruh effect says it is not. Particles are not little objects sitting in space waiting to be counted the same way by all. They are features of the field as carved up by a particular observer, and different observers carve the field differently. The field is the shared, underlying reality. The particles are how that reality looks from a given state of motion. Change the motion, and you change the count. This is perhaps the clearest statement of why the field, not the particle, is the bedrock. If the number of particles can depend on the observer, then particle number cannot be the deepest layer of reality, because the deepest layer should not shift depending on who looks. The field can be the same for both observers while the particle count differs, which tells you which of the two is the more fundamental description. The particle is real, but it is a derived and frame-dependent way of describing the field, not an absolute inventory of what is there. The Unruh effect is fantastically hard to observe directly, because the accelerations needed to make a noticeable bath are enormous, far beyond what we can easily arrange. It remains for now a firm prediction of the theory rather than a measured fact, and honesty requires saying so plainly. But it is woven tightly into the same mathematics that gives us results we can check, and it is the close cousin of an effect that has reshaped how we think about gravity, space, and the fate of the most extreme objects in the universe. For if motion can conjure particles from the vacuum, then so, it turns out, can gravity, at the edge of a black hole. If an accelerating observer sees particles in the empty vacuum, then gravity should do something similar, because one of the deepest insights of physics is that acceleration and gravity are two faces of the same thing. Stephen Hawking followed this thread to the edge of a black hole, and what he found in 1974 startled even those who had thought black holes were the simplest objects in the cosmos. Black holes, he showed, are not perfectly black. They glow, faintly, with particles born from the vacuum at their rim, and over unimaginable spans of time they slowly evaporate. A black hole is a region where gravity is so strong that nothing, not even light, can escape from within a certain boundary called the event horizon. Cross that boundary and there is no return. By the older picture, a black hole could only grow, swallowing whatever fell in, never giving anything back. It was the perfect trap, the darkest object imaginable, and it seemed it should sit unchanged forever unless fed. Hawking, applying quantum field theory to the curved space around the horizon, found that this is not quite true. The reason reaches back to everything we have built about the vacuum. Empty space near the horizon is, as always, the restless quantum vacuum, the fields trembling at their lowest energy. But the horizon does something drastic to how that vacuum is described. Just as acceleration changed the particle count in the Unruh effect, the extreme warping of space at the edge of a black hole changes what the vacuum looks like to an observer far away. The quiet vacuum near the horizon, seen from a distance, appears to contain a steady outflow of real particles, streaming away from the black hole as a faint thermal glow. This is Hawking radiation. A common way to picture it is to imagine the vacuum's activity right at the horizon producing pairs, with one member falling into the black hole and the other escaping outward to become the radiation we could in principle detect. The picture is vivid and widely told, and it captures something real about energy balance. But as with virtual particles, the honest caveat is that this cartoon is a simplification of a subtler calculation about how fields behave in the warped space around the horizon. The radiation is real, and its properties are calculable. The little story of splitting pairs is a helpful image laid over deeper mathematics, not the literal mechanism. The consequences are profound. Because the escaping radiation carries energy away, and because a black hole's energy is its mass, the black hole slowly loses mass as it radiates. It shrinks. Given enough time, far longer than the present age of the universe for any large black hole, it would radiate away entirely and vanish. The perfect trap leaks. The darkest object glows, and the temperature of that glow depends inversely on the black hole's mass, so that smaller black holes are hotter and radiate faster, ending their lives in a final bright flare. Hawking radiation has not yet been observed from a real black hole, because the glow from any black hole we know of is far too faint and far too cold to detect against the noise of the universe. This is a genuine limit, and we state it without dressing it up. Yet the result rests on the same field theory that has been confirmed to 12 decimal places elsewhere, and it has reshaped physics by tying together gravity, quantum fields, and the vacuum into one puzzle. It stands as a towering example of what the field picture makes thinkable, that particles can be born from empty space at the edge of a hole in the universe, simply because gravity reshapes what the vacuum means. We have come a long way from the solid spec. The picture we have built is powerful, confirmed to staggering precision, and it underlies all of modern physics. A fair listener might now ask whether fields are the end of the story, the true bottom layer at last, or whether they too might turn out to be ripples of something deeper. Honesty requires admitting that we do not know, and that there are serious ideas suggesting fields are not the final word. The trouble that drives this question is that the field picture, for all its success, is not complete. The standard model of fields describes 3 of the 4 forces beautifully, but it leaves out gravity. Our best theory of gravity, Einstein's general relativity, describes it not as a field of particles but as the curving of space and time itself, and that description has resisted every attempt to fold it cleanly into the quantum world of fields. When physicists try to treat gravity as just another quantum field, the infinities return and refuse to be tamed by the renormalization that works so well for the others. Somewhere in the marriage of gravity and the quantum, the field picture as we have it breaks down. One leading attempt to go deeper is string theory. Its central idea is simple to state, whatever the formidable mathematics behind it. Perhaps the fundamental things are not point-like ripples in fields, but tiny vibrating strings, far smaller than any particle, and each kind of particle is a different note that a string can play. An electron would be a string vibrating one way, a quark a string vibrating another, a photon yet another. The different fields in this view would all be different patterns of one underlying kind of object. A string and gravity would emerge naturally alongside the rest. It is an elegant hope, and it has driven decades of deep work. A different attempt, loop quantum gravity, takes space itself as the thing to be quantized. Rather than placing fields on a smooth backdrop of space, it proposes that space is not smooth at all, but woven from tiny discrete pieces, a fine network at scales far below anything we can probe. In this view, the smooth space our fields live in is itself an approximation, emerging from a deeper granular structure, the way a smooth fabric is really a weave of threads when you look closely enough. Both of these and other ideas alongside them share a common spirit. They suggest that fields, like the particles before them, may be an excellent description at the scales we can reach, while resting on something more fundamental underneath, some deeper structure from which fields and even space emerge. We have made this move before. The atom gave way to the electron and nucleus. The little ball gave way to the field. It would be in keeping with the whole history if the field gave way in its turn to something deeper still. The crucial honesty here is that none of these deeper ideas has been confirmed. No experiment has yet seen a string, or the grain of space, or anything below the fields. The scales involved are so fantastically small that testing these proposals directly is beyond our present reach, and may stay so for a long time. They are serious, mathematically rich attempts to go deeper, and they are also, for now, unproven. The field is the deepest layer we have actually confirmed. What lies beneath it, if anything, remains open, and a calm mind holds that openness without either dismissing the ideas or believing them ahead of the evidence. We are near the end, and this is the place to gather the open questions plainly, without dressing them up and without pretending they are smaller than they are. A picture this successful can tempt us to think the work is finished. It is not. Several deep things remain genuinely unknown, and naming them honestly is part of respecting the idea rather than overselling it. The wonder is more durable when it is true. The first great unknown we have already glimpsed, and it is sharp. When we add up the zero-point energy of all the fields, the trembling baseline of the vacuum, and ask how much it should weigh, how strongly it should push on the expansion of the universe. The calculated answer is larger than what we observe by an enormous margin, one of the widest gaps between prediction and measurement anywhere in science. The vacuum's small local effects, the Casimir push and the Lamb shift, come out exactly right. Its total weight comes out catastrophically wrong. Something basic about how vacuum energy and gravity fit together is missing, and no one yet knows what. The second is the one we just met. Gravity has not been brought into the quantum world of fields. General relativity and quantum field theory are each superbly confirmed in their own domains, and they do not fit together. At the places where both should matter at once, the centre of a black hole, the first instant of the universe, we have no working theory at all. The field picture, for all its reach, falls silent exactly where the questions are deepest. There are more. We do not know why the fields have the particular masses and strengths they do, why the electron weighs what it weighs, why the forces have the relative power they have. These numbers are measured and fed into the theory by hand, not explained by it. We do not know what most of the universe is made of, since the matter described by the standard model appears to be only a small fraction of what gravity tells us is out there, the rest being dark matter and dark energy, whose nature is unknown. And underneath it all sits the old puzzle we never fully resolved, the measurement problem, the question of why and how a spread-out wave function yields a single definite outcome when we look. Hold all of this calmly. It does not undo what we have built. The field picture is not made doubtful by these gaps, any more than the roundness of the Earth is made doubtful by an unmapped valley. We have established to extraordinary precision that particles are excitations of fields, that the vacuum is restless and has measurable effects, that mass comes from the Higgs field, that the count of particles can depend on the observer. These are not in question. What remains open is what lies beneath the fields, how gravity joins them, why their numbers are what they are, and what the dark majority of the universe is. The known and the unknown sit side by side, and a steady mind can carry both at once. This is the honest shape of the science. We have replaced a 2,000-year-old picture with something far truer, and that truer picture comes with its own frontier of open questions, as every real picture does. The wonder does not live in pretending we know everything. It lives in seeing clearly how much we have learned, and how much genuine mystery still waits past the edge of it. With that honesty in hand, we can return to the simple question we started with, and answer it as plainly as the science allows. We began with something solid in your hand, a cup or a coin, pressed firm beneath your thumb, and a simple story about what it is made of, down and down to a final speck, a smallest ball of stuff. We can now answer the question that Story was reaching for, the oldest question about matter, in the plainest words the science allows. What is a particle, really? A particle is a ripple in a field. It is one quantum of excitation in a field that fills all of space, spread out like a wave and counted like a lump, closer to a sound than to a stone. The smallest piece of you, and of that cup, is not a tiny ball of matter at all. It is a disturbance in something that is everywhere. Walk back through how we got here, because the path is the proof. The atom, once thought uncuttable, was opened by Thomson and emptied by Rutherford. The electron inside it refused to behave like a ball, spreading through both slits, blurring its place and motion, carrying a spin that does not spin. The little ball failed at every test, and in its place we found the field, with the photon as its ripple, then the electron, then quarks, and the rest, every particle a quantum of some field filling the universe. The vacuum turned out to tremble, and we measured its tremble. Mass turned out to come from an ocean of field we cannot see. Even the count of particles turned out to depend on who is looking. At every step the field proved the truer thing, and the particle proved its ripple. So the firmness you feel under your thumb is real, but it is not what you thought. It is not solid stuff packed tight. It is force, the electrons in your skin and in the cup pushing apart across mostly empty space, and those electrons are themselves ripples in a field that stretches across the whole universe. You're not built of tiny marbles. You're a pattern of excitations in fields that fill all of space, a standing arrangement of ripples held together by other ripples that carry the forces between them. The matter of you is the same fields, rippling, that make the distant stars. There is a strange comfort in this, once the surprise settles. The little ball was lonely, each speck its own separate object, scratched and singular. The field picture is the opposite. Every electron in your body is a ripple in the very same electron field that carries every electron in every star, identical to all the others because they are all excitations of one shared thing. The same handful of fields humming everywhere at once make the page in front of you and the light reaching you from across the galaxy. You're not a collection of separate grains adrift in empty space. You're a momentary shape in fields that are continuous with everything there is. The science is not finished, and we have said so plainly. We do not know what lies beneath the fields, or how gravity joins them, or what the dark majority of the universe is made of. The frontier is real and wide. But what we have learned is real too, confirmed to a precision that still astonishes, and it has quietly remade the oldest picture we carried about the world. The last uncuttable grain that Democritus dreamed of turned out not to be a grain at all. Press your thumb to the cup once more. What is under it is not the end of a long road of cutting. It is the universe, rippling in the shape of a thing you can hold.